Hello, marvelous Algebra 1 students, and welcome back to our second lesson in Topic 8, Polynomial Operations and Factoring. We learned last class what polynomials were, and we learned a little bit about them. We learned how to add and subtract them, and actually our next three lessons, 0.02, 0.03, 0.04, are going to be all about multiplying. We're going to approach multiplying from a couple different perspectives as well. And we are looking at our first daily learning target, which says I can multiply polynomials using the area or box, or even sometimes you'll hear it called the array method. So let's start with our opener here. Your goal is to find the overall area of each shape below. And you'll notice that each shape below is a four-sided shape. 90-degree angles in the corner. That means these shapes are called rectangles. On some of them, the rectangles are split into smaller rectangles. For example, this one has 2 rectangles, this one has 4, and so on and so forth. Our goal for each one is to find the total area, the whole area around the outside. And I would like you to do that by finding the smaller areas first. Okay, we'll talk a little bit more about that in a second. However, do you remember how to find the area of a rectangle? Most of my students do, and there's a couple ways to say it. Sometimes you'll hear this said as area equals length times width. That's a cursive L. Oftentimes you hear it as base times height. They really mean the same thing. So please go ahead and find the area of each of these. You will notice that some of them have x's. These last 3 in particular have a bunch of x's here. When you have x's like that, your area is going to be in terms of x. And I'm going to write that over on the side for you. When you hear in terms of x, that means that there will be an x in your answer. Yeah, so these answers aren't going to be just numbers. They're going to have x's there as well. All right, so go ahead and pause this video, work the opener, chat with each other, take a few minutes, and then once you're comfortable or once you guys reach a stopping point, unpause the video and we'll see how you did. Ready, set, go. All right, you're back. So I'll try to go through these pretty quickly. I know especially the first few are not too terrible. There are a couple of things I do want to show though. So on the first one, you would have done 7 times 3. You could have done 3 times 7. It's the same thing, and that is 21. So our area here is 21. Now our second one, we would do 7 times 2, which is of course 14. And then for this guy over here, we'd multiply these two, right? And that would give us 7 times 3, which is 21. Now from this point, I get 2 questions from students. They say, well, wait, do we multiply these numbers together or add them together? Well, the way that I don't want you to do it, but it's a nice way to check your answer, is we could say, well, if this is 2 and this is 3, technically this 2 plus 3 on the top is adding together, and it means the whole top side is 5, right? This whole top side up here is 5. And so we could, I'm going to say, quote, cheat, and say that the whole area here is just 7 times 5, which is 35, right? Now, since we know 35 is the right answer, let's work backwards and see what we have to do with 14 and 21. Do we multiply 14 times 21? I don't think so. I think to find our total area, we take this piece, which is 14, this piece, which is 21, add them together, and that will give us 35 as the final answer. Yeah, you add the individual areas to find the total. All right, so when we do our next one, we'll go a little faster. This gives us 12, 4 times 3, 3 times 2 is 6, 5 times 4 is 20, 5 times 2 is 10, and then we take these 4 pieces. So we have 12 plus 6 plus 20 plus 10. We'll try to be efficient here. 12 and 6 is 18, 20 and 10 is 30. 30 plus 18 I think is 48 for the total area. A quick check, this is 8 times 6, and 6 times 8 is 48. So I know that way is a little faster. However, we can't always do that way, because once we get to these guys down here, you'll see that they don't always combine together. So let's try 7 times 3x's. This means you have 7 of those 3x's. So you could say 3x plus 3x plus 3x. There's 3, here's 4, 5, 6, and 7. And the reason I'm doing this is because oftentimes people say, well, wait, 7 and 3x aren't like terms. We learned last class that if you have 7 plus 3x, they don't go together. That's your final answer. It's a binomial. And you're right. But multiplication is a little bit weird here, because multiplication, when you first learn this, it's actually defined as something called repeated addition. So 7 of these 3x's actually means 3x plus itself 7 times. And when you're adding these 3x's, aren't these all like terms? 3x plus 3x plus 3x plus 3x. They are. So 3, 6, 9, 12, 15, 18, 21. It turns out that we can multiply pretty much anything together that we want. 7 times 3x actually gives us 21x. So our area here is 21x. Now, people say, well, what does the x stand for? Well, the x could stand for anything you want. You could make x 7, and then 3 times 7, this is actually 21. You'd replace this x with 7, and it'd give you the total area. But for now, we're just keeping it in terms of x. Let's try another. Okay, 7 times 2x. Well, instead of writing out 2x 7 times, let's just multiply to say 14x's. 7 times 3x, we saw earlier, is 21x's. From here, we have 14x's, 21x's, and we can add those together. We actually did this addition earlier, and that's 35x's. That's our final area. Last one, trickiest of all. Well, let's do the ones we know for sure. 5 times 2 is definitely 10. Okay. 3x times 2 is certainly 6x's. Okay, I'll kind of box those so we can keep track. Right? 5 times 4x is certainly 20x's. But what about this last guy, 3x times 4x? We're going to have to be careful here. So I'm going to write this out first. 3x's times 4x's. And what we need to remember is that multiplication can be written in any order. And there's actually a lot of multiplication here. 3 is attached to x by multiplication. 4 is attached to x by multiplication, which means I can reorganize this any way I'd like. I can do a 3, and then the 4, and then the x, and then the x, and that means the same thing. And now, multiplying this isn't too bad. 3 times 4 is, of course, 12. And let's dig deep and go back to our last 2 units. How do we write x times itself? That's right. That is x squared. And so 3x's times 4x's, we really multiplied the 3 and the 4 to get 12. And then we did the x times the x to get x squared. And this is a very common situation that's going to come up today and really every lesson for the rest of this unit. So let's take our individual pieces. I have my 12x squareds. I have my 20x's, which are positive. I have my 6x's, which are positive, and my 10, which is also positive. Are we done? Well, we should look for some like terms, and I'm just going to use the small space down below. Doesn't this bring into what we did last class? There is no like term with the 12x squared, but 20x and 6x are like terms. That is 26x, and then the plus 10 at the end. And so my final answer is 12x squared plus 26x plus 10 written in standard form. Isn't it cool how this area actually tied into last class? Multiplication became addition at the end. So, without further ado, your teacher should be passing out a set of algebra tiles for your group. And I think I have enough in our class so that every group of 2 people can get a set of algebra tiles. You're going to have to work with somebody else. Gasp, I know. You can pretend to like them for a few minutes for today. We're going to use algebra tiles quite a bit this unit. And I like them because they give a very good visual, first, of the area model. A lot of multiplying polynomials can be tied back to finding area of rectangles. And second, they do a really nice job of showing that x squared, x and 1s are not like terms. That's kind of like this answer we got before. I had 12 of these x squareds, 26 of these x's, and 10. We could say these are 10 1s if you want. 1 plus 1 plus 1 plus 1 is all the way up to 10, right? 10 1s. And they don't go together. They're not like terms. So go ahead, pour out those algebra tiles on your desk, and then decide which each shape is in terms of, is the shape a 1, an x, or an x squared? Talk about it with your group quickly. I'm still going to keep talking over you. And actually for today and for the next couple of classes, I'm just going to use some digital algebra tiles. I'm going to draw these ones first, but then I'm going to jump over to the digital tiles just because I think it's a little faster, a little bit more clear, and honestly, I just get sick of drawing all of them all the time. You guys, it's easy. You can move them around your desk, not too bad. All right. Now, I found in the past that most groups do a really nice job of identifying those algebra tiles. The 1s pretty typically are yellow, and they're shaded in. I'm not going to shade it, though. The x's, I think on yours, are greens, and if they're not, though, they're the ones that look like these kind of long, skinny tiles. And then the x squareds, not so shockingly, form a square, but they're a big square. They look like this. Now, we're also going to quickly identify the lengths and the areas of each side. So it turns out that the 1, the x, and the x squared are actually the area of each rectangle. So let's fill those in first. This has an area of 1, this has an area of x, and this has an area of x squared. Now, how do you find the area? Because these are all rectangles, aren't they? Well, area is base times height. So let's see if we can figure out what the bases and heights have to be here. And I'll do those in black just so they can fit in. Well, to make 1 for the area, doesn't the base have to be 1 and the height has to be 1? Right? Area is the base times the height, which gets us that inside value. Okay, so that means anytime you see this distance, it is a length of 1. Now, sometimes students ask, 1 what? Is it centimeters, inches? Oh, well, we just say 1 unit. Just 1. That's it. We don't actually have a specific unit. So if you look at this x over here, do we know 1 or 2 of the sides here already? Well, if you take this yellow tile and you put it up alongside the x, isn't that yellow tile going to perfectly fit along one end right here? And that yellow tile, since it has a length of 1, doesn't that mean then that this green tile also has a length of 1? Actually, I'll do that on the top, just so I don't run out of room. And then we ask ourselves the question, well, if area is the base times some height, and we know the answer has to be x, then what is the height of this tile? Well, the height of this tile has to be x. 1 times x is x. 1 times anything is itself. And so the height of this tile we say is x. Using that, we can fill in our x squareds, because we can look at the lengths of the sides and we can say, well, what do we know about those? Is there any shape we know so far that fits here? Well, put one of your green tiles, one of your x tiles along the x squareds, and you'll see that it perfectly matches a side, which means the side of this must be a length of x. And if you take your green tile and you line it up along another side, you'll find it perfectly fits as well, which means the top of this is also x. And that isn't a surprise, because if you take x and multiply it by x, what do you get? Well, x times x is written as x squared. Now, here's a no-no. Try to take that same green tile and try to put it across your x squared tile. You'll notice it fits pretty well, but they don't fit perfectly. You can fit a few of these on here, and then one of them ends up hanging off at the end. And that's on purpose. We can't substitute some number of green tiles for a blue tile. There isn't a replacement here. In fact, the only thing we're going to do with these tiles is we're going to be fitting them around the outsides of others. They never go on top, they just go on the sides. So go ahead, please, and separate your algebra tiles by size. And you want to make it so that your teacher can visually and quickly count the number you have. So a lot of times students will take the ones and they'll put like, a whole bunch of ones like this, and then they'll put a whole bunch more ones up here in a row so you can quickly count and say, oh, that's 12 ones because it's 3 by 4. Now, as a heads up, you should have the following number of algebra tiles, and I put these together every year. You should have 6 of the blue x squareds, you should have 10 of the x's, and 25 of the 1's. If you have more than any of those, let your teacher know now. Once your teacher has picked up any of the extras, now, if you are one of the groups where you don't have enough, let your teacher know and they will give you extras there. You need to end with the same number of tiles at the end of class. So that means if a few of your tiles accidentally end up on a neighbor's desk, you're going to have to rectify or fix that number. If tiles end up accidentally falling on the floor, you'll need to pick those up. So keep track of them, please. That is going to be your exit ticket. All right, now, with this being said, let's get a little bit more into the algebra tiles so we can talk about why the heck we're using them. So, using algebra tiles is an easy way to visualize polynomial operations. Now, you can do it with addition and subtraction. We'll do a quick example there, but we're going to mainly use them for multiplication and then later on division. So we talked about the 3 tile sizes. We didn't talk about the red sides. You'll notice if you flip any of your tiles over, they become red. That means they are negatives. So if you have a blue side facing up, that is a positive 1x squared. If you flip it over, that represents a negative 1x squared. If you had 2 of these negatives next to each other, and I know those aren't squares, then there are 2 of those negative 1x squareds, and so that's representing negative 2 of those x squareds. If you have a tile like a green one, and then you put a negative in front of it, you need to flip your tile over to red. If you have 2 negatives in front, you flip it to red, and then you flip it back. A negative is an opposite or a reverse sign. We already talked about part D. You can border an x squared tile with an x, so you can put an x on the side, right? However, you can't replace x squareds. X's only go on the sides. And that's the same thing with the 1's, right? If you have this x tile that's up here, you can put a 1 tile at the bottom. However, you cannot put 1 tiles on the sides. They won't perfectly fit. They're not designed for that. So, let's do a little bit of practice. The first thing I'd like you to do is, without algebra tiles, go ahead and simplify this expression below. This is back to last class's lesson. Once you're done, write it in standard form, and then let your teacher know so they can quickly check. You're going to unpause, and we'll see how you did. Ready, set, go. All right. Well, this one shouldn't be too terrible. We know that there's that invisible 1 in front, so we can drop our parentheses here, 4x minus 6. And then on the other one, we learned we have to take this negative and we distribute. And remember last class we said the negative is like an opposite sign. So it's just going to flip the signs of everything in there. Looked like a negative 3x squared, so it becomes a positive 3x squared. Was a positive, becomes a negative. Was a negative, becomes a positive. And then last but not least, we had to combine like terms. I showed this once last class, but I'm going to do it this class. I'm going to put the like terms next to each other. We have 2x squareds, and that's going to sit next to my 3x squareds. So I took care of those. Then I have positive 4x's, and it's going to sit next to the negative 3x's. Last but not least, I have negative 6 of those 1's, and then positive 2 of those 1's. Once we're here, we combine them together and see how many we have. So 2x squareds plus 3x squareds mean we have 5 of those x squareds. Okay. 4x's minus 3x's means we have 1x. You can write the 1 or not. And negative 6 plus 2 gives us negative 4. Change that really quickly. There we go. All right, let's go ahead then and see how to model that with algebra tiles. So with your group mate working with you, one of you is going to take your algebra tiles and is going to model 2x squared plus 4x minus 6. You're going to lay those out on your desk. Your partner is going to lay out negative 3x squareds plus 3x minus 2 on their desk. Go ahead and do that, and I'm going to try to match the same here. I'm probably going to have to flip back and forth a couple times, but it's not too bad. Let's see here. So we had 2x squareds. So I'm going to do 2x squareds. And they don't have to be perfect here. I'm just going to kind of put them next to each other. So then we had positive 4x's, I think, and then minus 6 at the end. So there's 2, 3, and 4. Mine got a little messy. That's fine. And then we had 6 of the ones. 1, 2, 3, 4, 5, 6. So this models our first expression. Oh, but no, it doesn't, because these are supposed to be negatives, aren't they? Ah, drat. We had all that. I wonder if I can erase them all at once. No, unfortunate. Okay, these ones are all supposed to be reds. I don't know why I'm erasing. Oh, no, I do need minus 2. That's unfortunate. So if you didn't put them as reds, go ahead and flip them over. I'm going to do the same thing once I learn how to erase a little bit better. There we go. Oof, slower, but I think still faster probably than writing them all. Let's go ahead and snag some reds. So 1. And I'll just keep these out because I'll be needing them later on. 2, 3, 4, 5, and 6. Awesome. Okay, the other one was negative 3x squared. So here's what should be on your partner's desk. 1, 2, and I'm just going to put this down below. Negative 3x squareds, 3 x's, positive this time, lovely. 1, 2, and 3. And we finish off with a minus 2. 1, 2. There we go. Okay, so we have 2 different expressions. You could think of them separate. They're on 2 different desks, not a big deal. And once you guys are looking pretty good there, I would like you now, please, to perform the operation 2x squared plus 4x minus 6 minus the second one. Now remember, if you are subtracting this second one over here, what does that mean you have to do with all of the tiles there? Well, a minus means do the opposite of every tile that is there. So to do the opposite, we are literally going to change these to the other color. Okay, so to change them to the other color, I'm going to go ahead and unfortunately delete these. It'd be nice if I was able to click, and maybe I'll find a better way to do this next time, just to flip those tiles. Nothing on the other side let me do that, but I'm going to go ahead and change those colors. Now you guys hopefully could do this very quickly. You just need to take them and flip them over on your partner's desk. Now 1, 2, 3 looks pretty good, and then we had to flip these, and I don't remember how many there were. There were 3 x's, so I'm making them negative 3 x's, not too bad, and we had to flip these, and I believe this will become positive 2. Now we're not done though. Technically, all the tiles here are my answer, but this answer is actually equivalent to what I have over here. And that was not my final answer. My final answer was everything simplified. So let's see how we can simplify these algebra tiles. We're going to put them next to each other. All right, there's 1, 2, 3, 4, and look at my 5x squared. So you guys are going to pick one desk and you're going to slide them over. Now what about the x's? Well, we can set these right next to each other if you want. However, what's going to end up happening with our algebra tiles is whenever you have a negative and a positive of the same color, you can set them on top of each other, but what's really going to end up happening is they're going to cancel out. A negative and a positive cancel. So you can see here that there are going to be 3 sets of canceling. So I'm going to cancel 1, 2, and 3. Then I'm going to go ahead and do the same thing with my tiles, with my ones rather. I have 1 and 2. We're going to cancel those, so I'm going to get rid of them. When I say get rid, you're just going to put them back to your original pile. Don't actually throw them away. We need to save these. And let's see what we have left now. It looks to me like we have 1, 2, 3, 4, 5x squareds, 1x, and minus 4 of those ones. And does that match? 5x squareds, positive 1x, and minus 4 ones. It does. Now you're probably saying, wow, that was a lot of effort to just do basic addition and subtraction. And you're right, it was kind of silly to do. However, multiplication makes a lot more sense, and this is extremely important. So let's go ahead. Problem 3 gives us a rectangle that has a width of x and a length of 2x plus 3. And I think it really illustrates why I mentioned that I don't like using width and length earlier on. Does width mean this way? Does it mean this way? Which way does length mean? And so instead of using width and length to describe the outside of a rectangle, I'm going to go ahead and change these to base and height. And you don't have to do that. It's going to mean the same thing. But what we're really going to do right now is we're going to draw a rectangle that has a base of x and a height of 2x plus 3. And we saw that before on the opener, but let's go ahead and take a peek. So here is a rectangle. We've decided to change colors halfway through. It's very exciting. And the base is x. We could also say this base, same thing as x. And then the height is 2x plus 3. Now, there's a few ways to put 2x plus 3. We can do 2x plus 3 like so. And you could even do this, and this is kind of strange, but instead of 2x's, wouldn't you agree that 2x's is an x plus another x? That's 2x's plus 1 plus 1 plus 1. Isn't that kind of a weird way to write 2x plus 3? It's the same thing, though. And maybe you're getting an idea of why I split it that way. I split it that way because using algebra tiles, we have x's and 1's at our disposal. Now on the opener, we kind of split this 2x and this positive 3. I'm going to rewrite this again, a 2x and a positive 3, or we could even do it this way. Traditionally, x is up here, 2x and 3 like so, and we kind of did a little dashed line to find the areas, right? You can put the plus in front of the 3 if you want. It doesn't make a difference. We know it's there. And that's what we're going to do with our algebra tiles. Traditionally, with algebra tiles, we have a top and then a left side. We don't need to put the right side in the base because this is a rectangle. We already know that if you have a top and a side, a base and a height, what the other two are. They're equal to the top and the corresponding side. So my rectangle is just going to look like this. So go ahead and pull out some algebra tiles. We're going to need x, that's the green one, 2 more x's, so 2 more greens, and then 3 1's. And I've shockingly already prepared this so that I don't have to agonizingly slowly move them across the screen. So here we go. I've got these over here. Now we're going to build our rectangle. Okay, this guy up here is going to be x. Notice this has a length of x right here. Then to make our rectangle, I'm going to do it wrong at the first place. I don't want to put this guy right here. Right? That's this length from this little corner where my mouse is down to here is not a length of x. It's missing this piece up top. I need to actually slide this down to be right in the corner. So this is x, this is another x. My rectangle, though, is 2 x's tall, so here's another x, and then 3 1's. And we're really trying to line these up pretty closely here on your paper. 1, 2, and 3. And when I say on your paper, I mean on your desk. This outlines a rectangle that has a base of x and a height of 1x, 2x, 1, 1, 1 of 2x plus 3. Now you could continue outlining the rectangle. You could put another x down here, and then you could put 3 1's and 2 more x's along the side. There's 2 reasons we don't do that. 1, you don't have to. We can already see the outline of the rectangle. And 2, it kind of just wastes algebra tiles, and you don't have that many algebra tiles. So we try to really use the fewest algebra tiles we can. So this outlines the rectangle the same way that we did here. Now, when part B says use algebra tiles, draw your representation below, you should actually do that, right? On your paper, you should draw something here. You label the inside with x, and then you have an x and an x, and then you should use your space better than I did, and a 1, and a 1, and a 1, right? This shows x and then 2x plus 3. Now, our goal is to find the area of this rectangle. We can actually find the area using algebra tiles without doing any math, right? On the opener, we had to multiply these guys to find the inside, and it wasn't too hard. But we can do the same thing here. So what I'm going to do, to find the area, I'm going to take algebra tiles that represent the answer. We do need to be a little bit careful about the signs. This is a positive x and a positive x. And when you multiply, because that finds area, when you multiply 2 positives together, it stays positive. What goes in here? Well, it needs to be a shape that perfectly fits the two sides. And you'll notice that x squared perfectly fits those two sides. Now we're doing x times this x down below. That's another x squared. And then we have x times 1. I need a single shape that fills this. Hopefully you can see it's another x, and an x, and a third x. And so our final answer here, the inside of the rectangle is built by how many of these x squared shapes? Well, it's built by 2 of those x squared shapes, and we can really draw the inside of our rectangle too, right? I'm going to do this right now, and I'll do a better job than before. Here's an x, and then we had our 3 1s, right? 1, 2, 3, something like that. And then we had the x hanging out up above here. So the inside of the rectangle that I'm going to do is an x squared, and I'm going to fill these in so we can see them. An x squared, and then we had, I'm just going to cheat here, that's supposed to be in green, but that's all right. And we had our x and our x and our x. So the inside of my rectangle has 2 of those x squareds, and then 3 of those x's which are positive. So the inside of my rectangle is 2x squared plus 3x. Now, symbolically, what did we do? Well, we found the area of the rectangle. An area is found by multiplying the base, which was x, times the height, which is 2x plus 3. And when we multiplied those out, the standard form was 2x squared plus 3x. So this was the problem. It had parentheses. This is the answer. It didn't have parentheses. Now, of course, it does get a little tedious to model this with algebra tiles over and over and over again, and we're going to look at faster ways to do it. One way that's very common is known as the box, or sometimes the array, or sometimes the area method. Area, obviously, because we just found area. So there are 2 ways to demonstrate this box or area method. I'm going to actually show the way on the right first, and then we'll work back to the box method option 1. So on the right here, what you would do is you would draw a rectangle, and you'd split it into 2 parts. Why 2 parts? Well, because the top was x, and then the height was 2x with a positive 3. Once you're here, we would have to find the insides. And the insides, because this is area, are found from multiplication. So this guy here, you would do 2x times x, and you usually wouldn't show that step. We saw before 2 times x times x. The 2 has nothing to multiply with, but x times x makes x squared. And then, down below, we would have to do 3 times x, which is just 3x. Now, there is a second way to do this as well. You'll notice that this rectangle is turned on its side. And even though that I said x was the base and the height was 2x plus 3, does that matter? Well, I don't think so. It's just the same thing as switching the order of these two, and since it's multiplication, we're allowed to switch the order. So, am I allowed to put x here and 2x plus 3 here? Certainly. When we multiply these, x times 2x is 2x squared, x times 3 is 3x. Don't forget, though, that's not the final answer. Just like the opener, we take the 2x squared, and we take the 3x. It's positive. We put them next to each other. See if there are any like terms. There aren't, and so we're done. Not bad, right? Let's try one more. A rectangle has a width of x minus 2 and a length of 2x plus 3. Why don't you guys pause me for a second and see how you guys do using algebra tiles to model this situation. You're going to be drawing your representations, just so you remember. You don't have to draw them every time, no worries, just a couple examples. And you're going to fill in the rest of this just like we did on the first one. So pause me once you've had a chance to do parts A through E, unpause, and we'll see how you did. All right. Hopefully things were successful. I'm going to try to model this for you as well, and I'll do the outline first. 2x plus 3 and x minus 2. So I have 2x plus 3. That's still the same side here. I just went with the height. 1x, 2x, 1, 2, 3. 2x plus 3. And then I did an x with a minus 2. Did you remember to make yours red because they're negative, x minus 2? When you're drawing this, by the way, because sometimes you do have to draw this, it's not too terrible. And again, I'm just going to zoom in and do my best here. We have, I'll kind of use this space here. We had 1, two x's, and then 1, 2, 3. Because you're not working in colors, I like to just put positives and negatives on here. So we have positive x's, positive 1's, and then we have over here a positive x, and then we have this minus 2. So that's a nice way to show it. Okay, now it says write an expression using a product, product means multiply, to model the area of the rectangle. Well, area is going to be x minus 2 times 2x plus 3. And notice again, you could have written that the other way too, 2x plus 3 times x minus 2. If you were given this problem and asked to multiply this out or asked to find the area, you might struggle a bit. This is something we actually haven't done before. But using the algebra tiles, it's not that bad. And I'm going to quickly show you on my side. So I need to fill in this inside area. Remember, I left that cut out of the corner with tiles that actually fit the space. So these ones, like before, are going to be my x squareds here, right? We have 2 of those x squareds. And like before, we have 3 of these x's. But then things get a little bit trickier going the other way. Did it throw you guys off? Well, going down here, can you visualize the shape? And honestly, sometimes drawing it is a little bit easier. You can go through and kind of do dashed or dotted lines, and I'll zoom back in again here, all the way across. And then you can do them going down too. And that gives you a nice visual of the shapes that should be fitting in. These 4 guys right here look like X's, but vertically instead of horizontal. Also, we are doing a negative times a positive. Anytime you have 2 tiles where one is red and one is not red, the resulting answer is always going to be red, because a negative times a positive is a negative. Think of the opposite of a positive. Same thing here, the opposite of a positive and the opposite of a positive. What about these 6 at the bottom? Well, we're doing red times yellow, red times yellow, red times yellow, and that means that all of these at the end are going to be negatives. So fill these in on your desk, fill in your drawing as well, and then we'll talk about what this answer looks like in numbers. There we go. So, our area then, okay, multiplied out is going to be, well, we have 1, 2, we have 2 of these x squareds, so that's not bad. Then we have 1, 2, 3 of these green x's and 4 of these red ones. So I have 3 green x's and 4 red ones, which means they're negative. And last but not least, we have 6 of those 1's, which are negative. Are we done? Well, that is an answer, but we're not in standard form yet because we haven't combined all of our like terms. Luckily, there aren't too many like terms to combine here, but there are a couple. Notice you can take the greens and cancel out 1, 2, 3 reds. It leaves you with 1 red left, which means there is negative 1 of those x's remaining. This is known as the expanded or the standard form of the area of our rectangle. Now again, it gets pretty tedious to have to write out all these algebra tiles, so we probably need a faster way to do it. And the faster way is to really, instead of writing x and x, write it as 2x. Instead of 1 plus 1 plus 1, write it as 3. And we do that by making a 2 by 2 box or array. Okay, so we're going to go ahead and take this 2x plus 3 and x minus 2 and work it in here. We had a 2x with a positive 3, and we had an x with a negative 2. Now this always throws people off, and we'll tackle this one first. Remember, the inside of each of these are rectangles, and the inside of a rectangle, the area of a rectangle, is always found by multiplication. So this bottom right box is found by multiplying positive 3 and negative 2. Multiply, not add. A lot of people say with 3 minus 2, that's 1. We multiply to find the inside. And 3 times negative 2 is actually negative 6. Multiplying the rest, 2x times negative 2 is negative 4x. X times 3 is 3x. And 2x times x is 2x squared. Now, you'll notice that there are two boxes shown because the base and the height don't matter for the order. So I could put the 2x and the positive 3 up here and the x minus 2 down below. When you multiply, 2x squared, 3x, negative 4x, and negative 6. Sometimes students will ask, can we switch the order that these are in? And yeah, you can. Traditionally, though, we like the x's on the upper left corner, and the one on the lower right doesn't have the x's, and there's going to be a little bit more reasoning for that later on. For now, though, the reason we do that is because on algebra tiles, seriously, the upper left, the x squareds are always diagonal from the ones, and on the lower left and upper right, the x's are always diagonal from each other. So as long as you can keep that, you'll keep making these rectangles, and you'll be good to go. Okay, are we done? No, we need to take the interior of the box and combine like terms, right? So our area then is 2x squared. There's a positive 3x and a minus 4x, and then there's a negative 6. And combining like terms, we get 2x squared minus 1x minus 6. All right, the last part of today, I know finally, right, is you are going to be working with another partner at your group with Algebra Tiles, and you're going to do the problem twice. Your partner is going to model the problem using Algebra Tiles, and they're actually going to draw the Algebra Tile model on their paper. You are going to model it using the box method, like we did up here, box or array or area method, whatever sounds good. And you're going to make sure that your answers match. Then on the next problem, because there are 5 of these, you're going to switch methods. So now you're going to take over for the algebra tiles, and your partner is going to do the box method. And I'm going to demonstrate one of these for you really quickly, just so you know what the heck I'm talking about, and then you guys are on to it for the rest. By the way, there might be a problem on here somewhere where the algebra tiles aren't going to work for the model, and at the very end, I'll show you what that looks like too. Okay, so go ahead and let's do one example right now. And actually, why don't I do the example that doesn't work for the algebra tiles? That makes sense. I'll skip right to the end, and then you guys can try the rest. So if you tried to do this last one with algebra tiles, I think you'd run into a bit of an issue, because this x plus 1 here, you would draw something like, and I'll just do it over here, you'd have your x with your algebra tile, right? And then you'd have your 1, so that seemed to work okay. And then I've run out of room here, so I'm actually going to use this bottom space here. Then you'd have to border this with an x squared tile, and then an x, and then a 1. And that's a really funky looking rectangle, right? This guy doesn't work. In fact, the only way you can do this is you actually have to make this 3-dimensional. Bonus points if you can figure out how to make these go 3-dimensional. And so you'll find that if you have an x squared in the problem, this algebra tile thing isn't going to work. You can still do it though. We're just going to have to use the box method. So our box method starts by, shockingly, drawing a box. We still want to think of this as like a base and a height. So my base is x plus 1, my height is x squared plus x plus 1. I know, having experienced this a few times, if the base has fewer terms than the height, the base only has 2 terms, then I want to make, ooh, that was not good, I want to make a pretty skinny base here. Okay? So when I do a skinny base, this is going to be a rectangle that has a smaller base than it does a height. I'm going to give myself a little bit more room here. There we go. Now my base has 2 terms. It has x and a positive 1, which means my rectangle is going to be split into 2 columns. But the height has x squared, positive x, and a positive 1, which means the height is going to split my rectangle into 2 more divisions. And so when we split something in 2 and then split it into 3 more, that's actually going to give us 6 spaces. How do we find the interior of each space? Well, we multiply. So, and I'll try to keep my like terms and colors, x squared times x will give us x cubed. Okay, x squared times 1 will just give us x squared, and I can put the 1 in front if you'd like. X times x will give us x squared. We'll put the 1 as well. then x times 1 will give me 1x. 1 times x will give me 1x. And 1, not plus, 1 times 1 gives me 1. If you set this up correctly, and both of these are in standard form, biggest exponent to smallest, you'll find something pretty cool happens here. I'm going to write out all the terms once up above. There was an x squared, or an x cubed rather, and then diagonally, notice that there are 1x squared plus another x squared. They're both positive. Then diagonally, we have 1x and 1x, and then at the end, we have this 1. Yeah, if you set these up in the standard form, a lot of times this box method will give you like terms on the diagonal. So then, writing our final answer, there is nothing like the x cubed, so it stays. X squared plus 1 more gives us 2 of those x squareds, just like last class. We have 1x plus another x, that's 2 x's. And finishing off, we have this 1 at the end. Okay, so you have 1, 2, 3, 4 of these to do. You can do all the rest of these with algebra tiles and using the box method. The box method is like what I did down here. I drew a box, right? So please do them and switch off to make sure you're comfortable. We're coming back to those algebra tiles several times. Check with your teacher once you're done. Okay, and then you can go ahead and sort your algebra tiles by size, just like we did at the beginning, so your teacher can quickly see the number you have and recount them and verify they match your starting number. Once you are done with all that, you can unpause the video and see if you got the answers right. I'm just going to give you the answer, not the work to get there. And that's about it. Ready, set, go. All right, you're back for these. I'm at least going to show you the setup for each one. Not too much work in between though. This has 2x and then there's an x plus 3. If you did everything right, you'll get 2x squared plus 6x. Hooray! You could have, of course, set this up the other way. You could have set it up so that it was 2x up top and x plus 3 on the side. Our next one, x minus 1 times x plus 1. X minus 1, x plus 1. If you do everything right, you're going to get like terms. You're going to get x squared plus 1x minus 1x, forgot the minus 1x minus 1. Combining like terms will give you x squared plus 0 x's, which we don't need to write, minus 1. That's the most simplified form. Our next one, another 2 by 2 box. A lot of ours will be 2 by 2s. We need a lot of practice in here. 2x plus 1, x minus 1. This will give us 2x squared. I started writing there. We should probably just do the answer. When you combine your like terms, you're going to get negative 1x, or just negative x, and then minus 1 at the end. Last but not least, set up that box. Negative x plus 1. That's going to be a little different than what we've seen before. When you multiply this out, you'll get negative 3x squareds, right? And then you're going to get positive 1x, or just plus x if you will, and then a plus 2 at the end. All right, hopefully you found some success today with this box method. Next class, we're going to use fewer algebra tiles. I know, don't groan too loudly. And we're going to focus more on different ways to do this multiplying besides the box method. So tune back in to lesson 8.03 next class. Thank you. It's always a pleasure, and I'm excited to watch you succeed.